Hello, you're welcome back to my channel. In today's lesson, we're going to consider the life cycle of stars. And at the end of the lesson, you'll be able to understand the fact that looking at a star is looking back in time. And you'll be able to appreciate how distance from the Earth to different stars are measured, and also be able to explain how stars are formed. You will also be able to explain how a star such as our sun gets its energy to shine. Okay? And you'll also be able to explain the different phases of the life cycle of stars. Looking back in time, we see objects because light from them enters our eye. Light from the sun takes about 8 minutes to reach us. This implies that when you look at the sun, you are seeing it how it were 8 minutes ago. Light from a distant star, such as the Alpha Centauri, takes 4.3 years to get to us on Earth. This means that when you observe the distant star, like the Alpha Centauri, it means you're seeing it how it were 4.3 years ago. Light from some galaxies, stars in some galaxies, takes a billion or even more years to get to our galaxy, or even our planet. Okay? When you look at the night sky, you are looking back in time. Light from some stars, like I said earlier, take up to a billion years or even more to get to us. Okay? This means that some of the stars we see today have even get to the end of their life cycle. Okay? Now, we need to appreciate the fact that light travel at a finite speed of 300,000 kilometers per second. How far is the farthest planet? Or how far is the farthest star from the Earth? Recall that I told you earlier that light travels at a finite speed of about 300,000 kilometers in 1 second. Okay? This implies that 300,000 kilometers is equivalent to 1 light second. When I multiply it by 2, like in this case here, 2 times 300,000 kilometers, which is 600,000 kilometers, then I will have the equivalent as 2 light seconds. For a light year, it means I have to multiply the 300,000 kilometers by the 365 days of the year by 24 hours of a day and 3,600 seconds of an hour to give me something close to 9.5 trillion kilometers. Okay, so it implies that 1 light year is equivalent to 9.5 trillion kilometers. Some galaxies are billions of light years ahead of us. Okay, this will give us an idea of how large the universe is, or how far some stars are from us. Okay, light from the sun takes 8 minutes or 500 seconds to get to us. We can therefore say that the sun is 8 light minutes or 500 light seconds ahead of us. Okay, now when you do the maths involved, you will discover that 500 light seconds is equivalent to 150 million kilometers. Okay, and that distance is what we call the astronomical unit. Okay, an astronomical unit is actually the distance from the sun, our very sun, to the Earth. Okay, so 1 AU, which is astronomical unit, is equals to 150 million kilometer. 150 million kilometer. Okay. Now we use the astronomical unit to make comparison, to compare a lot of distance of celestial bodies. Okay. Star formation. Now, before we talk about star formation, we need to understand this, what a nebula is. A nebula is just a cloud of dust and gas. We can sometimes call it interstellar cloud of dust and gas. In some nebula, gravity pulls the gas together to make a star. Okay, this implies that before a star can be formed, gravity needs to pull the nebula together. Okay, need to collapse them together to be able to form a star. Now, this particular nebula that form a star are actually called the stellar nebula. It means we have others. Okay, the region or the area where we have this dense nebula coming together, contracting, is what we call the stellar nursery. So I can refer to this region here as a stellar nursery. But it is worth to note that a ringed nebula is not a stellar nursery. It's just a planetary nebula. Okay? A planetary nebula is actually formed when a red giant has shedded a lot of its mass, its outer layer, into space. Okay? Stellar nebula is an area of outer space within a dense nebula in which gas and dust are contracting, resulting to the formation of new star. Stellar nebula are the clouds that form the new star. And remember, I told you some facts about the composition of this cloud. There is hydrogen, helium in it, plasma, and dust. So when they contract, we have a birth of a new star. How does the sun get its energy to shine? Now, this is a wonderful process. A sun actually gets its energy to shine by this special kind of reaction, which we call the nuclear fusion reaction. In this kind of reaction, hydrogen atom combine together, fuse together to form helium, a different element. Okay? And tons and tons, a large amount of energy is released in the process. Helium produced during the reaction fuse to make other elements. Elements up to I in the periodic table are made in stars like our sun. Now, we need to know that the temperature and the pressure needed for nuclear fusion to take place in the sun are all contained in the center of the sun, okay, or the star, as the case may be. The sun has enough fuel to keep shining, okay, like what we've seen today in the next 5 billion years to come. Okay? Our sun actually is classified as a small size star or a yellow dwarf star. Okay? So you can imagine how other stars could look like. We have stars as big, much more bigger than our star, than our sun. Okay? The life cycle of the different types of stars. There are 4 stages in the life cycle of a star. The first stage is called the birth stage. The second stage is the main sequence stage, followed by the old stage, and then the death and remnant stage. Okay? We're going to discuss this stage in the slide. Now, the birth stage. Like every other thing in the universe, the sun has a beginning and its end. Okay? Now, for the birth stage, the sun or any other star is born from a cloud of gas and dust, which we call the stellar nebula. Okay? Now, for the main sequence stage, gravity pulls the gas together to form a main sequence star. Massive stars like Sirius are formed. In some cases, low mass stars like the Sun or medium mass stars are also formed in this stage. Now we have the next stage, which is the old age stage. The star at this stage grows to what we call a red giant. And if it's a massive star, it becomes a red supergiant. Now the death stage. At this stage, the outer layer will be thrown into space, okay, because most of its fuel or most of the gas involved in the nuclear fusion reaction have been spent, so it releases its outer layer into space, which we call the planetary nebula. Okay, for a red supergiant, there's going to be an explosion, uh, which is referred to as the supernova. Now, the remnant stage. At the remnant stage, the center will shrink and become a white dwarf and then cool off to become an invisible black dwarf. Okay? Now, for a massive star, it's either a neutron star, a neutron star will be formed, so filled with a neutron, or a black hole will be formed after the supernova. Now, we need to note this, that other heavier elements, elements that are much more heavier than iron in the periodic table, are usually made at the supernova explosion, okay? The remnants of the stars are flung into space to form nebula. This nebula produce new stars when they gather together at the stellar nursery, okay? Now the summary of the life cycle of a star. The birth stage. We have collections of clouds here. The clouds are mainly the composition of hydrogen, helium, dust, plasma, and so on. These combined together are pulled together to form protostar and then Titari phase. Now, at this stage, we have the birth of a new star. Then the main sequence stage. In the main sequence stage, we have a low and medium mass star shining like this, our sun, or a high mass or massive star shining like Sirius. Notice the difference in color. That tells us the difference in temperature also. Now the old age stage. After most of the gases or most of the fuel needed for nuclear fusion reaction have been spent, the sun or a star will expand to become a red giant. And if it's a massive star, it becomes a red supergiant. Okay? Now, the next stage, which is the death and remnant stage. At the death stage, the red giant sheds off its outer layer. Okay? And we'll have what is known as a planetary nebula with an inner core. Now, notice the white stuff, something right inside here. Okay? Now, for the supernova, there's a large explosion that releases all the matters, elements that are contained in the star. Okay, leaving behind the neutron star or a black hole. Okay, now for a medium-sized star, we have a white dwarf left behind, which further cools off to a black dwarf. Guys, I believe you understand the lesson. If there's anything you need me to adjust or to add to the lesson or to add in my subsequent lesson, please leave a comment on the comment section. Have a nice day.